Hey everyone, in this video I'm going to be explaining the paper that I've been working on for the last year titled Statistical Analysis of Earth's Evolutionary History Suggests Earth is Likely the Only Civilization in the Observable Universe. Okay, to prove this I'm going to be using the following method that is basically centered around two ideas, the first of which is the 30% rule. So the 30% rule is the notion that if you take into consideration that Earth took 3.8 billion years to go from single-celled organisms that got more and more complex until they eventually became primates, and if you take into consideration that the sun is getting hotter and in 1 billion years will be hot enough to render Earth uninhabitable, then we can deduce that any aspect that sped up Earth's evolution by 30% or 1 billion years was crucial to happen for civilization to exist on Earth. Second idea is the principle of mediocrity. So because the principle of mediocrity basically states that if we pick something at random that has multiple categories, we're more likely to pick one of the more numerous categories than one of the less numerous categories. And this basically applies to the 30% rule, because if we pick a random civilization and examine all of the aspects in that civilization that follow the 30% rule, we would expect all aspects that follow the 30% rule to happen in the most likely way possible rather than the least likely way possible. And that gives us the ability to estimate the probability of civilization happening in the universe, because all we have to do is calculate the cumulative probability of all 30% rule aspects that happened on Earth. And we can use that as a rough estimate to figure out the general probability of civilization in the universe. Okay, so I'm going to be focusing on three major events in Earth's history that follow the 30% rule. I've already made two videos where I go into depth and a lot of detail about these three events. So in this video, I'm mostly just going to be estimating the probability of these three events. So first, I'll explain why these follow the 30% rule. So the dinosaur extinction event happened right here. This time frame is the period where dinosaurs existed. This is where the first mammal existed. And throughout this period, mammals were very small and completely dominated over dinosaurs. And then this event miraculously killed all the dinosaurs while leaving mammals alive. And then in this small time frame of mammal dominance where dinosaurs didn't exist, mammals created civilization. So the dinosaur extinction event follows the 30% rule because dinosaurs cannot create civilization. And we know this because based on the principle of mediocrity, if dinosaurs could create civilization, we would expect to be dinosaurs and not mammals. Okay, that was kind of simplified, but if you're curious on more of the details of that argument, then you should watch the previous video. So the second event that follows the 30% rule is the Devonian Tetrapod Transition. This happened basically from here to here, these two upticks in extinction. So civilization must take place on land. I know this because if it was possible for civilization to happen underwater, then we would be a civilization underwater, because that would be more likely, because fish are a more likely occurrence than fish becoming tetrapods and then going on land and then becoming mammals and then creating civilization. So it would be more likely, because life originated underwater, that if civilization was possible underwater, that we would be underwater. So civilization must take place on land. Therefore, the transition from fish to tetrapods, which happened basically by fish turning their fins into legs, that must have happened for civilization to exist. So that also follows the 30% rule. And then finally, Theia's collision was the creation event of our moon, where Earth crashed with a planet, and the debris from that collision created the moon. And essentially, this collision, based on the evidence that we have, was perfect in every way, meaning Theia had the correct elemental composition, They hit us at the correct angle, it hit us at the correct velocity, etc., etc. So these three events are very unlikely, and I'm going to be using the principle of mediocrity to estimate the probability of these events. Okay, the first event I'm going to be looking at is the dinosaur extinction event, because this event we have the most data on, and I can get the most accurate estimation, so I can use this to kind of compare. But anyway, so there are four significant things in the fossil record to understand this event. The first thing that happened 66.25 million years ago, the Deccan Traps started erupting. And then basically this is a mantle plume that started erupting. And then just 150,000 years later, a gigantic impactor hit. So big, in fact, that this created an 11 magnitude earthquake, which was 9 magnitude at this distance, which would have made this eruption go on for even longer. Additionally, the Chicxulub crater is right on a sulfur deposit, so we know that because this this asteroid hit this exact spot, there was an extreme cooling effect that resulted because of all these sulfur was released into the atmosphere. And then, after that, the next most significant thing is the Shiva crater, which was a impactor that hit the Deccan Traps. So basically, what the Chicxulub did with 9 magnitude earthquake would have been many orders of magnitude stronger when the Shiva impact hit, because now I'll go over the sizes. So Shiva was proposed to be 40 kilometers in diameter, making it the largest impact ever recorded on Earth's history. And then the Chicxulub was about 10 kilometers in diameter, making it like one of the top 5 biggest. And then the Boltish crater was only 1 kilometer. So for that reason, I'm not going to be calculating the Boltish crater as like a significant event, because I don't see how it really compares to these two, because this hit a sulfur deposit, which was very important because it created an extreme cooling event that would have killed a lot of dinosaurs. And then this was important because just like the Chicxulub crater, the earthquake created by this impact would have prolonged the Deccan Traps eruption and made it much, much stronger. Basically, I'm going to be taking these 3 events and calculating the probability of them all happening in a 1 million year time frame, which is what we observe. Okay, so the Deccan Traps is about a type of like volcanism that would happen maybe once every 100 million years. So the probability of this happening within 1 million year time frame is 1 in 100. So we can basically apply this logic to all the events that happened. So the Chicxulub impact was a like 1 in 1 billion year occurrence. So this would be a 1 in 1,000. I say this because there are about 5-ish Chicxulub-sized impacts that we have evidence for in Earth's history. And then for the sulfur deposit, I'm not 100% sure about what this exact probability would be, but I know that it's very unlikely that the Chicxulub impact would happen to hit a sulfur deposit. So I'm going to estimate that this is 1 in 1,000. And then Shiva, although it is bigger than Chicxulub, I'm just going to lump it as a 1 in 1 billion year incident. And then Shiva just so happens to hit the Deccan Traps. This can't be a coincidence. Therefore, I'm going to lump this in with sulfur deposit and say it's a 1 in 1,000. And finally, all of this needed to happen while dinosaurs were in a state of dominance. So, and while mammals were alive. So this basically happened for 100 million years before this event happened. So to make this 1 in 10, the assumption would be that dinosaurs would survive at least another 350 million years before either the sun got too hot or a different extinction event killed them. So yeah, basically all of these things happened to kill dinosaurs and allow mammals to live. So basically the principle of mediocrity would say that all of these things must have happened must have needed to happen in this like specific situation for this to work, because because of the principle of mediocrity, like if it was possible that volcanism could kill dinosaurs while leaving mammals alive, it would make like way more sense for volcanism to have caused this mass extinction. So the fact that it was caused by like this crazy set of multiple impacts all happening at the same time suggests that this was like the only way that mammals could have survived while dinosaurs died. And the probability, if I take a look at all of these aspects, comes out to 1 in 10 to the 15. Okay, so the next event I'm going to be talking about is the Tetrapod Transition. So the best way to understand how the Tetrapod Transition relates to the principle of mediocrity is to ask yourself the following question. If you give fish an arbitrary amount of time to evolve, are they naturally just going to turn their fins into legs? Or scenario 2 is that fish will not naturally become tetrapods, and the only reason they did is because specific events made that transition more likely. So as we can see, there are two significant events that happened during this transition. The Kalwasser event is basically an event where we know that ocean anoxia happened, meaning there was minimal oxygen in the ocean for a temporary amount of time. And this event 359 million years ago is called the Hangenberg event. And during this, there was ozone depletion and also anoxia yet again. So I read a paper that said the Hangenberg event was caused by a supernova, and it looks like, based on the evidence, that this could be true because we observed that the ozone was depleted and anoxia, and that would be two like possible outcomes of a supernova, which would like shoot radiation and destroy the ozone layer. So if we look at the fossil record and where these events fit in, there is a very, very strong correlation that these events aided the transition. So if we look at Tiktaalik, Tiktaalik is basically the first known fossil of this transition. And Tiktaalik happened 375 million years ago. Then, 3 million years later, the Kalwasser event happened. And the next fossil we see in the fossil record, we see that there's a dramatic difference between Tiktaalik and Acanthostega. So basically, what I would argue is that the anoxia created by the Kalwasser event did a couple things. One, because Tiktaalik was a lunged fish, it incentivized Tiktaalik to keep his head above the water, because Tiktaalik can no longer use his gills to get oxygen from the water, so obviously he would use his lungs more often, which would also incentivize Tiktaalik to basically like waddle around in the shallow water. So I propose that this is the reason that Tiktaalik's weird looking fins transitioned from this to this. Additionally, because the ocean was anoxic at this time, we would also expect there to be less competitors for Tiktaalik, the lunged fish, because most fish don't have lungs, so they would basically just be screwed. So Tiktaalik would have less competition and would be incentivized to waddle around in the shallow water. So I propose that this is why Tiktaalik transitioned to Acanthostega. And then we have these, basically Acanthostega, Ichthyostega, and Tulerpatin. These are the only fossils we have like immediately before when the supernova might have happened, and then everything else over here is after the supernova. So the main difference between these two is that these were like aquatic animals that had fins that were very convenient for walking, and these are fully terrestrial tetrapods that like are not really aquatic. So this is basically when the transition is officially over. And it also just happens to coincide with the supernova that would have happened exactly at this time frame. We have Paderpes 359, Greer-Pertin 359, and everything else is post supernova. So just like the Kalwasser, the anoxia would have helped these guys out by removing competitors and incentivizing them to walk around. However, I think there's more to it, because what we know about the supernova is that it would have essentially shot ionizing rays for 100,000 years, specifically gamma radiation. And gamma radiation can damage DNA, which would mean it would essentially create a faster, more mutation, so possibly a faster evolution speed for 100,000 years, which would essentially supercharge the evolution from this to this, because the faster mutation rate would create more variance in offspring, and then like the better ones would survive and pass their genes on, which would end up being these. So yeah, basically that's how I think the tetrapod transition happened, and it coincided with these unlikely events. So like principle of mediocrity, we would basically assume that these events had to happen in like the timeframes that they did for this transition to occur. And another argument on that note is the fact that these are basically the only fossils we have during this time frame, which would suggest that there is a limited population of this, which would enforce the idea that the transition would have failed without these lucky events. Okay, so calculating the probability is kind of a challenge because there's a lot we don't know. Like we don't really know 100% what the cause of the Kellwasser event was. However, I speculate that it was likely a large mantle-plume eruption that happened underwater. And I'm not the one who came up with this idea, but based on the evidence, this could have caused ocean anoxia, because if the eruption happened underwater, basically like the magma would bind to the oxygen in the water, which would just steal all the oxygen essentially from the ocean. So this could have been caused by a mantle plume, and my estimation for something like that would be 1 in 200 million years. And then for the time frame, I'm going to say 5 million years, just because it happened 3 million years after Tiktaalik started to exist. So I think 5 million years is a fair estimate. And then the ideal supernova, assuming this was a supernova, it would have to be like a really ideal supernova, because if the supernova was too strong, it might completely kill everything. And if it was too weak, it might not have the desired effect. So based on that, I'd say maybe a supernova this perfect would happen once every 10 billion years. And again, I'm going to be using a time frame of 5 million years. And then finally, all of this must happen when fish exist, which would be about 1/3 of Earth's history. So my final estimation for the probability of this event is 1 in 250,000. Okay. Theia's collision. So Theia's collision is the event that we have the least solid information about, of like the odds, but I'm gonna, basically what I'll do is I will explain all of these arguments and explain why I think this event is comparable to the dinosaur extinction event in terms of probability. So this collision could have happened in very, very many different possible ways. But based on what we know, the collision happened for us in the perfect way. So if Theia was bigger, it could have hit Earth into the sun, it could have destabilized Earth's orbit, it could have done really bad things. If Theia was smaller, we would have fewer volatiles, we would have less water, and both of these would be bad news. If Theia's elemental composition was wrong, it could translate to slow evolution. So basically there's, the perfect ratio. We might have had the perfect ratio of elements on Earth for all we know. And, what if the carbon to oxygen ratio was different, or the carbon to nitrogen, or anything? That might have had a drastic effect on Earth's evolution speed, just like it just could have. So we don't really know how perfect Theia's elemental composition was, but it could have been perfect, because obviously even the dinosaur extinction event was extremely, extremely unlikely. And the only reason we got that far was because Theia's collision was ideal. Theia's impact angle. If Theia had a different angle, if we had a shallower angle, we would have been closer to zero obliquity, which would be bad. Obliquity is basically axial tilt, and 23.45 seems ideal. because 0 is really bad because there would be no seasons and no averaging of the poles and the equator. And then 90 would also be extremely bad because it would mean that for like a quarter of the year, half of Earth would be in complete darkness. So 23 seems ideal because it's above 0, meaning we have the positive effects of averaging the poles and the equator, and we have minor seasons, but it's not so high that it would create like super dangerous seasons and also like really bad temperature swings. So this seems like an ideal axial tilt angle. So the question would be like, okay, what if this was 24? What if this was 25? Would that have a drastic effect or would that be negligible? We don't really know because we would basically need to have some simulation that can simulate evolution and like try different axial tilts. So like we really don't know how perfect our angle was either. But if it was a different angle, we would have a different obliquity. It's basically correlated. Again, also the moon's mass. So the moon stabilizes our axial tilt to remain at this level. So, and it also dragged our tilt to this level. So if we had a heavier moon, our tilt would have been closer to 0, which would be bad. If we had a lighter moon, it might not have stabilized our tilt at all, or we would have a much higher obliquity. And then Earth's spin before the collision. My idea of this collision is basically modeled on a model created by Dr. Stewart, and her model predicted that Earth had to be spinning very fast before the collision, possibly because of a different collision that happened beforehand. So this is very unlikely, and also because of the principle of mediocrity, we would have to assume that this was probably what happened. And that leads me to the final point, which is stable plate tectonics. So the more violent this collision would be, the better, essentially, our plate tectonics would be, because the more violent the collision would essentially correlate to Earth's interior being hotter. And the hotter Earth's interior is, like, the more strong the forces that actually move tectonic plates would be, because plate tectonics are basically moved around by the convection currents of the like liquidy super molten rocks in Earth's interior. So we would expect this collision to be as violent as possible. So for all these reasons, I am saying that this probability is comparable to the dinosaur extinction event, which is extremely, extremely unlikely. Unfortunately, we don't really know. So for now, I'm going to have the conservative estimate be 1 in 1 trillion, which is 3 orders of magnitude less than the dinosaur extinction event. All right. So the final thing that I'm going to be estimating the probability for is the solar system. And note that I'm not going to be talking about Earth. So basically any probability of Earth and Theia's collision, all of that, I'm just going to leave that in the probability of Theia's collision, and then everything else about the solar system I'll focus on. So the sun's mass. So the most numerous star is a red dwarf, and red dwarfs, not only are they much weaker than the sun, but they would also last much, much longer. Like a red dwarf will last trillions of years. So if it was possible for civilization to occur on a red dwarf, we would expect to be on a red dwarf, because it gives us much more time and leeway to evolve from single-celled organisms to civilization. So the fact that we are on a very hot sun star that is going to burn quickly suggests that this level of luminosity from our sun must be necessary for civilization. So the assumption would be that photosynthesis, well, actually, I mean, it's true that photosynthesis is very reliant on the sun's output, and it is more efficient. The more output our star has, the more efficient photosynthesis can be. So for that reason, I'm going to put the sun's mass and like luminosity at a probability of 1 in 10. This might be, I don't know, 1 in 20, but I think 1 in 10 is pretty fair. And the next important thing is the Jupiter and asteroid belt formation. So as we know, all of the impactors probably came from the asteroid belt. So the fact that Jupiter basically lies right outside the asteroid belt it basically maintains the asteroid belt in this specific location. And additionally, Jupiter is extremely massive and it's very close to the inner solar system. So Jupiter not only protects the inner solar system from anything from the outer solar system, but it also maintains the asteroid belt to like stay in that exact place near the inner solar system. So for that reason, Jupiter's gigantic mass and the location and maintenance of the asteroid belt, I'm going to estimate that the probability of that formation is 1 in 100,000. And then finally, the habitable zone of the Milky Way. We are in the outer region of the Milky Way, which means there is less star formation and supernovas and radiation and chaos that we would find in the inner Milky Way. So this is a positive because we would have less of that harmful radiation. So we have to, based on mediocrity, we have to assume that we would need to be in the outer region of the Milky Way, just because that's what we observe. So the probability of this is 1 in 2 million. The final conclusion of this presentation is that we are the only civilization in the observable universe. If we take the cumulative probability of all aspects in Earth's history that follow the 30% rule, that adds up to 1 in 10 to the 38 star systems. And notably, the upper estimate for the amount of stars in the observable universe is 10 to the 24. So, yeah. This also implies that if we look at the observable universe and compare it to the actual universe, it will probably just look like a minuscule speck of dust, because the actual universe could be many orders of magnitude larger than this number, or it could be infinite. All right, so that's the end. Thanks for watching. Hit that like button, hit that subscribe button, and yes, sir.